Hello and welcome to the Unit 4 podcast on section 10.3. Today we're going to be talking about reactions that occur in water. I'm Mr. Sakaguchi.
I'm Mr. Lin.
And let's start. So if we're talking about water, we're more specifically talking about solutions. So let's talk a little bit about what solutions are. Solutions are basically mixtures that consist of something known as a solute and a solvent. The solute gets dissolved, the solvent does the dissolving.
So when you have this solution, it happens to be in water. This is called an aqueous solution because the solvent is water. The solutes tend to be ionic or molecular solids, and they just get broken up into really small pieces. With the ionic compounds, they get broken into their constituent or the ions that make up the solid.
Yeah, so we'll talk more about the process of forming solutions as a separate unit, but basically with ionic compounds, they're this organized network, as we talked about previously, and then water, due to its polarity, surrounds each ion.
And pulls it apart.
Right. As we said before, some double replacement reactions produce precipitates or solids that come out of solution, and then this example here is written as follows. This is one way to represent a reaction like this, but remember we talked a moment ago about how ionic compounds dissociate in solution. So writing a reaction like this serves some purposes, but not always. There are some times where we'll actually take ionic compounds that are aqueous and dissociate them into their positive and negative components. When you do something like this, as I have written down here in this slide, or this part of the slide, this is known as a complete ionic equation. So notice how everything that is aqueous I have separated into ions. Notice though that the solid is not separated because since it's solid, it's not dissociating.
Right. Everything else breaks apart but the solid that's formed.
One other thing to point out here is the coefficients also need to be taken into consideration when you separate your ions. So because there's a 2 here, remember this means that there's 2 units of NaOH, so that's why I have 2 sodiums and 2 hydroxide ions. Because there's 2 chlorides for every 1 copper ion, that's where the 2 comes from for the 2 Cl minuses.
If you'll notice that in the end you'll have the same amount of sodium and chlorine in the reactant and the product side. As a result, these compounds, or sorry, these ions wind up negating each other. Kind of like in mathematics, if you've got a number or an x on both sides of the equation, they wind up canceling each other out. And that's what happens here. By the way, these ions are known as spectator ions. They kind of just sit on the side and don't really participate in the reaction that occurs. Hence, spectator. You watch a game, but you don't actually join in. As a result, you have what's known as a net ionic equation, written here at the bottom, where you have the ions that actually take part in the reaction to form your precipitate, your solid.
Yeah, so as Mr. Lin, as Mr. Lin said, these are spectators and they're not participating in the reaction. Now, this net ionic equation is basically just representing the reaction here and here, just presenting it from a different point of view. From an ion point of view, sodium and chlorine didn't really do anything different from where they were previous to the reaction, whereas the copper and the hydroxide ions became something completely different from changing from an aqueous state to a solid state. So there's some instances where this will be important to know.
Recognize that the sodium and the chlorine don't actually just disappear. What that really means is that they're just floating around, still dissolved in an ion form inside of the solution. They don't come back together to form NaCl aqueous. It's actually just sodium and chlorine ions floating around.
Right. There are some double replacement reactions that form water as one of the products. Sometimes the reaction looks like nothing actually happened, and there are other ways other techniques we'll use to indicate whether or not something's actually happened. In this case, we have an acid, HCl, and NaOH is something known as a base, something we'll talk about in the future, forming water and salt. Whenever you see an acid and a base, typically they'll form water as one of their products and a salt. And this is illustrated here. And if we take so this is the they call this the molecular equation or the balanced equation or complete equation. This is the
Complete ionic
complete
equation.
ionic equation. This is the net.
Right.
And this little figure kind of illustrates what's going on.
When you do this kind of reaction in a lab, you're not going to see anything different really as far as production of water. So like the water level in the beaker is not going to increase or anything like that.
Right. Other double replacement reactions form gases. You're not going to have to memorize every gaseous reaction, but you should memorize the common ones. The most common gases formed are carbon dioxide, hydrogen cyanide, and hydrogen sulfate or hydrosulfuric acid. One thing to note is this is carbonic acid or H2CO3. If this is one of your products, this is not the end product. Usually this product is very unstable and it'll react and decompose into water and carbon dioxide. So I never want to see H2CO3 as one of your products. You should immediately write out water and CO2. So for instance, here we have an acid, HCl combining with sodium, either sodium bicarbonate or sodium hydrogen carbonate, forming salt and H2CO3. Now because this is our product, we know that this thing will immediately break down into this.
Right.
Okay, and then we can rewrite our equation to kind of illustrate that happens. We can add these up and notice how, remember how we eliminated spectator ions previously? We can also eliminate compounds that appear on both sides of the arrow, like this, like these two reactions.
So when you put these two reactions together, you can add it up into one really long reaction. And then if you have the same compounds on the left and right, you can cancel them out and you get your net reaction at the bottom.
Yeah, and then you can, there you have it right there.
Yep.
Oh, and there's the elimination.
Well, there you go.